Hey everybody, this is Mr. Sheeline here. This is the video for the Unit 2.4 notes, the valence electron theory. Realistically speaking, just valence electrons in general. Let's just get straight to it. So the three objectives that I want you to be able to say that you can fulfill are these. You can identify the number of valence electrons found in the outermost shell of a particular element using the periodic table. You can understand the importance and function of the Lewis dot diagram, and you can also draw a Lewis dot diagram of a selected number of elements. Okay. So valence electrons, as we've talked about, Bohr saw that electrons must be arranged in specific numbers around the nucleus at different levels. These energy levels can hold a specific number of electrons depending upon the size of the nucleus. So shells, here are the shells and the max number of electrons they can hold. So the first shell can hold up to 2. The second shell can hold up to 8. Now these two we are going to be focusing on, as it says here, the little indicator on the right here. We will focus on these two energy levels because the next one's going to be 18. After that, it's 32. Okay. And then it can even go further than that, relatively speaking. But we're just going to be focusing on the first two there. So what is a valence electron? Well, a valence electron are electrons that are in the highest or the outermost energy level. Okay. That level is also called the valence shell of the atom. And for the most part, these electrons are held pretty loosely because it's the outermost. They're the furthest away from the nucleus. Okay. The number of valence electrons in an atom determines these two things. It more or less, it'll determine the properties of the atom. And it's more or less, it determines the properties of the atom because the number of electrons found in the valence shell will tell us how many protons that typically are found in it. So realistically speaking, you can infer. It doesn't determine. What determines it is more of the, arguably speaking, it's more of the protons. But what properties does it change? Well, these valence electrons change the type of ion. It can change, or it can tell you what type of ion, or if it'll become an ion. But also it tells us the way in which an atom will bond. Okay. So as a rule, the fewer electrons in the valence shell, in the outermost shell, the more reactive the element is. Okay. So as a good example, so the two columns to the left of the periodic table. So that's columns 1A and 2A. Those guys react pretty much with everything. So if you didn't know this, raw, pure potassium, if you add that stuff to water, I would just recommend look up videos on what happens when you take raw, pure potassium and you put it in water. Go look those up and see what happens. Okay. So when an atom has 8 electrons in a valence shell, for the most part, it's stable. Okay, it's happy. It's at equilibrium, relatively speaking. Atoms usually react in a way that affect the number of electrons. There are two ways that this can happen. Either the number of valence electrons increases to 8, or loosely how valence electrons are given up. So the good rule of thumb here, and something that we won't really get into, but just something to understand, is that it's easier. It's a question to always ask, especially when you get to chemistry. The question that I always ask my chem kids is what's easier, or with an atom that has a given, or an element with a given number of valence electrons, is it easier to give up or to receive? So a question would be like lithium. And as we'll get here in just a bit, lithium, I'll tell you, has one valence electron. And what we'll get into is that to make it stable, it needs 7 extra electrons. It needs 8 on that shell to make it whole, basically. So I'll ask you, what do you think is easier? Is it easier to get? Is it easier to gain 7, or is it easier to lose 1? More or less is the question. Again, it'll make sense here in a bit. We can determine the number of valence electrons on a particular element, or in a particular element, a particular element has, by using the periodic table. So the elements found in the A column. So if you look at your periodic table up at the top of each column, okay, or at least for a good chunk of them, it'll show that there are 1A, 2A, then it jumps, then it's 3 above boron, it's then 3A, carbon's 4A, nitrogen's 5, oxygen is 6, then fluorine 7, and then above helium there will be 8A. So the elements found in the A columns are those that have valence electrons that may be lost or gained. And you can determine the number they will either gain or lose by the number associated with the column letter. So it's not to say, though, that oxygen being in 6A is that it needs to gain or lose 6. Okay? It's to say this. Lithium is found in column A1. So that means, or 1A, sorry. That means that lithium has 1 valence electron in its valence shell. Chlorine is found in column 7A. Chlorine has 7 valence electrons in its valence shell. And what that last point there, that you can determine the number that they will either gain or lose, we'll get to that in a second. So, but let's first kind of practice this because this is still important. So, check your understanding. Number 1 here. Draw the Bohr models of these provided elements. Remember, the number of protons is equal to the number of electrons. So, draw. Let's now we know about these energy levels. Let's draw some of these Bohr models of these guys here, and I'm now seeing I've got calcium there twice, so that's cool. Okay, so pause the video here, draw these on your own, and then come back to make sure you've got them correct too. Okay, so let's try these out. So I'm first going to do carbon. So carbon here, carbon's just going to get just this. I'm just going to do this nice and simple. I'm going to say, actually, I'll say those are my neutrons, and I'm going to plot out all of my, or no, carbon's small enough. It's 6. God bless. So here are 1, 2, 3, 4, 5, 6. And then those are my protons, 1, 2, 3, 4, 5, 6 neutrons. Okay. So for the Bohr model, to keep with these energy levels, so 2 are going to go on the first level. Okay. Come on, man. That's aggravating. So that's 1 electron, 2 electron. Or actually, here, I'm going to do this. It'll just be way easier. The color of the shell will be blue, but the color of the electrons will be like pink. So 1, 2. Okay, and I know that there's 6 electrons. And the way I know it's 6 electrons because there's 6 protons. So there's 1, 2, 3, 4, 5, 6. Boom. Okay. Easy peasy. So here's my Bohr model for carbon. So let's take a look at calcium. Calcium's a little bit busier. So calcium has 20 protons, and I know that. Remember I know that because calcium has an atomic number of 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I know that's not 20. It's not showing up. My stylus is not doing as well as it should be right now. So if it's got 20, if it's got 20 protons, that must mean then it's got 20 electrons. Okay. Yeah, that's good enough. So let's see what this Bohr model will look like. So there's 1, 2. So only 2 can fit on the first energy level, and then 1, 2, 3, 4, 5, 6, 7. That's 1, 2, 3, 4, 5, 6, 7, and then 8. That's all we can fit there. And then the next energy level. So, and that's going to be, that's 1, 2, that's 10. So now we need to put 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, Oops, I did not distribute those as well as I should have. Oh, wait a minute. Wait a second. Here, give me 1 second. Okay, I don't know what happened to all my drawings here, but real quick, I'll redraw calcium. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20, yeah. We're going to draw 1, 2, 3. 2 on the inside, 1, 2. There's going to be 8 on the outside. This next level, 1, 2, 3, 4, 5, 6, 7, 8. So I've got 2 and then another 8. So that's 10. So 10 on the outside. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the Bohr model for calcium there. Now, you're probably wondering, well, how is it then, if you're telling me that calcium is in 2A, that means that it has 2 valence electrons. How can it have 2 valence electrons if there's 10 on this outside, on the very outside here? Well, it follows a rule that we're going to be getting into in a little bit, so just be patient. It'll make more sense when we get there, okay? It'll make more sense when we get there. It's a little rule that maybe you've heard of, maybe you've looked at before. It's possible. And of course, I can't see. Real quick, I need to see what that last one is because I can't see it on my screen. Let's see. Helium. Helium is the last one. So helium here. This guy's he's a little bugger. So here we've got 1, 2. 1, oop. Off there. 1, 2. And if there's 2 protons, that means that there's pretty much only 2 electrons. So it's got 1 energy level here. 1, 2. And those would be the Bohr models for each of these guys here. So something that we should be somewhat familiar with. So easy peasy. Oop, and I got to erase all this. So let's continue on. So let's try this now. Write the appropriate number of valence electrons these elements have according to their column numbers. So do this on your own, but come back after you've done this and then see if you got these right. So pause the video here, try it on your own. Okay, so carbon. Carbon is going to be found in column 4A. So that means that there are 4 valence electrons for carbon. Phosphorus is found in 5A, so that means that it has 5 valence electrons. Chlorine is found in 7A, so it has 7 valence electrons. Eesh. Bismuth is found, let's see, where's bismuth at? Bismuth, where'd you go? I just had you, there he is. Bismuth is also found in 5, so it has 5 valence electrons. Thallium, where's thallium? Thallium. Ooh, actually, we're going to ignore thallium. He should not be in there. Sorry. Thallium should not be in there. Forget thallium. If you spent time on thallium, sorry, but forget thallium. Calcium is going to be 2A, so that's 2 valence electrons. Helium. So helium's a weird one. So how many valence electrons does helium have? Even though it's in 8A, it only has 2. Okay. So easy peasy. So the number, so to continue this idea, the number of valence electrons increases, if you notice, as you move across the periodic table from left to right. Okay. Scientists draw atoms to show how they chemically bond. They only draw the valence electrons, and to do this, they do this in order to see how well one bonds with another, what angles they'll bond with one another, and typically because the valence electrons are what are used to bond. Electrons typically don't bond using internal electrons. And real quick, what's a chemical bond? Well, it's the force of attraction that holds two atoms together as a result of the rearrangement of electrons between them. Okay. And to show all this and to do what scientists do, they draw what are called Lewis dot diagrams. And they draw these diagrams of the atoms to show just how many valence electrons they have, so they can easily show, how one element bonds with another. These diagrams include chemical symbols for the elements surrounded by dots. Each dot stands for every one valence electron they have. So all atoms want a full sequence shell, and that's that's usually 8 valence electrons. So think of it this way, even though the third shell holds 18, it's not that it always wants to go to 18 or it can't go to 18. So with like calcium there, calcium had 10 on the outside, but it's willing to lose 2 so that its very outside shell can hold 8. Like, it'd be super satisfied with 8. It would also be satisfied with 18, don't get me wrong. But realistically speaking, it would be better off with, and it would rather stick with 8 or stick with 16, whatever comes first. But realistically speaking, it's going to want 8 because it's going to be way easier. So all atoms want a full valence shell. That's usually 8 valence electrons because this is how it becomes stable. This is known as the octet rule. Atoms are willing to give up or take electrons to either have 8 electrons in their valence shell or none, so that the next lower shell is completely full, or the next valence shell has 8 in them. Either full or 8, because obviously the first valence shell can't hold 8. It can only hold 2. Negative ions, these form when atoms gain electrons. Positive ions, they form when atoms lose electrons. Okay. So let's talk about drawing these Lewis dot diagrams. So first you're going to write the chemical symbol. Next you're going to look on the periodic table, see what column they're in. You're going to use the column number to determine how many valence electrons that element has. And you're going to draw the dots around the chemical symbol and equally distribute the dots. Only draw 2 dots per face or side of the chemical symbol. So they would look like this. So 2 great tips. If you cut these in half, the way that these should be is that if you were to cut them in half vertically or horizontally, it should look the same on both sides. They should mirror one another. Okay, so meaning you need to evenly distribute the dots all around the chemical symbol. And then also plot the dots as if the chemical symbol is in a box. Each face of the box can hold up to 2 dots. So to kind of use neon there as an example, it'd be like neon is in this little box here. Okay, you see that? It'd be like neon being a little box. Here's 2, there's 2, there's 2, there's 2. Each face of the box can only hold up to 2 electrons. Okay. Now there is one exception to these rules, and it is helium, because helium already has its outermost valence shell filled. It is an 8A, but it only has 2 valence electrons. Okay. So let's do this. So properly draw the Lewis dot diagram. So let's try this out. You try this out on your own. Pause the video here, and then after you're done, play the video again to see if you got these right. Okay, so let's try them out. Okay, so let's see here. So sodium is going to be found in column 1A. So sodium is going to be easy peasy. It's just going to be a dot, just 1 dot. Aluminum is found in 3A. So it's going to have 3. So it's going to have 1, 2, 3. Okay. Sulfur here is going to be found in 6A. So it means it's going to have 1, 2, 3, 4, 5, 6. Chlorine is going to be found in 7A, so that means it's going to have 7. So 7 valence electrons, so it's going to be 1, 2, 3, 4, 5, 6, 7. Magnesium is found in 2A, so it's going to be 1, 2. Silicon is going to be found in 4A, so it's going to be 4, so it's 1, 2, 3, 4. And then argon, I almost said arsenic, is going to be an 8A. So it's going to have 1, 2, 3, 4, 5, 6, 7, 8. And then phosphorus here is going to be found in 5A. So that's going to be 1, 2, oh, wait a minute. Yeah, 1, 2, 3, 4, 5. Easy peasy Lewis dot diagrams all the way around. Now, you could make them look like this. So some of them, you can make them look like this. I wouldn't be opposed to you doing this for magnesium, though typically you don't want to do that. You can do that. Silicon is the same thing. You could do this. Okay. That's not an awful idea. What's another one? You could do this for aluminum. You could do like 1, 2, 3. This is super goofy. This never happens. So would I be mad? I'd be a little weirded out because this just looks way better. Same thing with magnesium. It doesn't really happen terribly often like this. It usually looks like this. But anyway, what's another one? Oxygen's not on here, but oxygen as an example. So oxygen, this can be a thing. It's kind of a weird thing, but anyway. Okay, and I believe that is it. So it looks like that is it. So if you guys still have any questions for me, make sure you ask. This is the last material up until the Unit 2 test, so make sure we get this down. Make sure we practice this. If you have any questions for me, please ask. If not, I'll see you guys in the next one.